Good morning, students. Today we are moving to the next unit, second chapter. That is the second part of stereochemistry. That is geometrical isomerism. Geometrical isomerism means the isomers having the same structural formula but differing in spatial arrangement of the atoms or groups around the double bond are termed as geometrical isomers, and the phenomenon is termed as geometrical isomerism. The geometrical isomerism is based on double bond, rotation of molecules or atoms, or arrangement of atoms or groups around the double bonded carbon atoms is known as geometrical isomerism. Geometrical isomerism is exhibited by carbon-carbon double bond molecule and also carbon-nitrogen double bond and also nitrogen-nitrogen double bond. These three systems exhibit geometrical isomerism. We already discussed about optical isomerism in previous chapter, that is about carbon-carbon single bond. Here we are discussing about carbon-carbon double bond, carbon-nitrogen double bond and nitrogen-nitrogen double bond molecules. The double bond present in these cases restricts free rotation around the double bonded atoms. So rotation means usually single bond is having free rotation. That's why they are producing rotational isomers. In double bond, it is strong than single bond. It is tightly bound, the double bond. That's why rotation around the double bond is some restriction will be there. So the restricted rotation is possible in case of geometrical isomers. Free rotation is not possible. So like rotational isomers, such kind of number of isomers are not possible in case of geometrical isomers. Only limited number of isomers is possible in case of geometrical isomers. Geometrical isomers, they are also known as diastereomers. So next is some conditions for exhibiting geometrical isomerism. The molecule must contain a carbon-carbon double bond. That is the first condition. Rotation around which is strongly hindered. Some hindrance is there for the rotation. That is the first condition to exhibit geometrical isomerism. Second point, each of the two doubly bonded atoms should have two unlike groups attached to it. So, like example, A, B. A, B are different groups. The two different groups should be attached to the doubly bonded atoms. That is the next condition. So third point, the formula, it have two arrangements in space which represent the geometrical isomers. Here you can see the diagram. In carbon-carbon double bond, two different atoms are there. In one side, in first picture, the same groups are group means here one group is represented as A and next group is represented as B. In first diagram, the same groups are arranged at the same side of double bond. That is, you can see upper side of the double bond, the same groups are arranged, and also the lower side, the group B is arranged. In the next diagram, that is second one, the same group, that is, you can see where the groups A is arranged, that is in the opposite side of the double bond. So it is known as trans. The first one is known as cis isomers mainly. So next we will move to the nomenclature of geometrical isomers. First, geometrical isomerism due to carbon-carbon double bond. First nomenclature method is cis and trans nomenclature. That means the isomer having the similar groups on the same side of the double bond is termed as cis, and if the same groups are arranged on the opposite side, it is termed as trans. Cis and trans is a Latin word. Cis means same, trans means across. You can see the example. First one, cis to butene and trans to butene. Here the hydrogens are arranged on the same side and also methyl groups are same side. And in trans, the same groups are arranged on the opposite side. Here another example, malic acid and fumaric acid. Next is EZ system. In EZ system, it is based on the priorities of the groups based on Cahn-Ingold preloop convention. This term you have already heard in the last chapter, that is in determination of configuration of optical isomers. We already known about relative and absolute configuration. In absolute configuration, there are sequence rule. R and S nomenclature is based on sequence rule and absolute configuration. So in that we have discussed about some sequence rule. In that we discussed one system, that is CAN called prelock scheme. Based on that, we are nomenclature in the optical isomer. So this numbering system, that is the priority system, is used in case of E and Z system. So why this E and Z system is applicable in geometrical isomerism? Mainly, in geometrical isomers, last in cis-trans isomers, we have discussed about two different types of groups attached to the double bonded carbon. If it is tri-substituted or tetra-substituted, we can also name this compound instead of cis and trans. The cis and trans system is not possible if the groups are different. So for such kind of compound, E and Z system nomenclature can be used. So in EZ system, the two groups attached to each carbon of the double bond is numbered in the order of priority. Priority is based on the atomic number. If the two groups of higher priority are located on the same side of the double bond, it is known as Z isomer. Z means susammen, it means together. If the two groups of higher priority are on the opposite side of the double bond, then the alkene is designated as E isomer. E means endogen, meaning opposite. So these are some diagrams showing that if high priority group, high priority means what we are numbering in first. See this example. In the structure bromine and chlorine, in one carbon it is substituted bromine and hydrogen. By comparing bromine and hydrogen, bromine is having the highest atomic number than hydrogen. So the first number will come to bromine and second number will come to hydrogen. In the second carbon, the substituents are chlorine and CH3. Anyway, chlorine is having the highest atomic number than carbon. So the CH3 group. So chlorine will get higher priority number 1. So in these two carbons, the higher priority groups are bromine and chlorine. If that groups are arranged on the same side, it is a disomer. If the high priority groups are arranged on opposite side, it is E isomer. These are some examples. You can see in the first one, it is 1-bromo, 1-chloropropene, alkene. And in this one, first carbon contains two substituents, bromine and chlorine. Bromine is having the highest atomic number than chlorine, so we can number bromine as 1 and chlorine as 2. And in the second carbon, here two substituents are there, CH3 and hydrogen. So which is having the highest priority? Carbon is having the highest atomic number than hydrogen. So CH3 group is given the number 1 and hydrogen is given number 2. So we can see where is the higher priority groups are arranged. The groups which is having the number 1 is arranged at the same side of double bond. So it is, we can name it as Z 1-bromo 1-chloropropene. And in the second diagram, the higher priority groups are arranged in the opposite side, so we can name it as E 1-bromo 1-chloropropene. And in the next second example, same groups, that is E. Same groups means same groups are arranged and also based on priority. Here also bromine is having great priority than chlorine, and also chlorine and compared to chlorine and hydrogen, chlorine is having the highest priority. If the highest priority groups are arranged on the opposite side, it is E, and if it is the same side, it is Z. You can number accordingly. So next is geometrical isomerism due to C double bond N and N double bond N. That is the next category of nomenclature. That is syn and anti system of nomenclature. You can see some diagrams here. In the first picture, the hydrogen and OH are arranged on the same side of the C double bond N. Then it is known as syn. If it is on the opposite side, it is known as anti. And also, if instead of hydrogen, if alkyl groups are there, the second set of structures, we can see R and R dash. Based on R dash it is syn, and based on R it is anti. And also third set of diagram is showing the nitrogen double bond compounds. If it is arranged in the same side, the substituent groups, it is cis or syn. If it is in the opposite side, it is trans or anti. That is syn anti isomerism. It is mainly used for the compounds like oximes. Oximes are compound having general formula C double bond NOH. You can see in this structure where is that C double bond NOH. Here that OH and hydrogen are arranged in the opposite side. It is known as anti-isomer. And if the hydrogen and OH are arranged in the same side, it is known as syn isomer. That is a configuration of oximes identified by prefixes syn and anti instead of cis and trans. That is the main thing. So oximes means oximes are produced from aldehydes and ketones carbene compounds on reaction with hydroxylamine. So the product formed is known as aldoxime or ketoxime. In aldoxime, the syn isomer in which the OH group of the oxime is on the side of the hydrogen of the aldehyde carbon. It is known as syn. In ketoxime, specify the group with respect to which the oxime or the OH is arranged in the same side. It is known as syn. So that is the difference between syn and anti, and also aldoxime and ketoxime. So from that examples, you may be knowing what is the syn and anti nomenclature. Thank you. That's about the introduction and nomenclature of geometrical isomerism. We will continue the next topic on the next class. Thank you.